Success on the battlefield often hinges on the ability to make critical decisions and, when necessary, trade-offs. The same applies to the virtual world. When you design the visual battlefield, you're subject to both the power and limitations of the networked simulation system. You can't afford to do everything, so you're going to have to make numerous and often complex trade-offs. When you understand these trade-offs, you can make the best use of your system at the best cost. A typical networked simulation system is one of many in the virtual world on the net at the same time. This system includes a crew compartment, computer image generator, audio generator, control and display interface, voice communications translator, host computer, and a network connection. We're going to focus on the computer image generator, or CIG, because this component can represent half the cost of a simulator. It's this subsystem that creates the images of the virtual world we'll be designing, training, and fighting in. At the heart of the CIG lies the visual database, a numeric representation of the world that the computer image generator uses to construct everything that we see: terrain, structures, soldiers, vehicles, weapons effects, time of day, and weather. These images are all computed and then painted as individual pictures some 15 to 60 times per second to make real-time moving images of the battlefield. Generating these views of the virtual world requires considerable power. In fact, most of the CIG's computing power is taken up building these views with polygons and painting them with pixels. A polygon is a flat surface with 3 or more sides. Every shape in our virtual world, no matter how simple or complex, is composed of 1 or more polygons painted with colored pixels on the display screen. Pixels are the smallest elements the eye can discern. Ordinarily, they blend together, but under magnification, the pixels seem to form a very fine checkerboard, with each individual square assigned its own color by the CIG. These, then, are the basic building blocks of our pictures. What we will see in our pictures is determined by 2 major factors: viewpoint and field of view. Viewpoint, where we're looking from, and in what direction. And without moving our viewpoint, field of view is how much of the database we can see. What we see in our picture also depends on terrain fidelity, how close to reality the terrain database is built. A simple surface takes less processing than a more complex one, but the complex one may leave less power to put things on the surface. The closer to reality, the more computer power spent. How we will see or paint these pictures, and with what fidelity to real life, is governed by many other factors. Some of these are the number of viewports, frame rate, database density, viewing range, number of moving objects, display resolution, pixel color, texture, and level of detail. All involve computer power. With the number of viewports, for example, the computer power used is directly proportional to the number of different views generated at the same time. Twice the viewports, double the needed power. Frame rate is how often the computer renders the scene. Increase the rate, and the demand for power rises proportionally. Compare these areas of the scene. The left side uses less computer power than the right. Here is a scene with the same viewpoint and field of view computed out to 900 meters, 2.5 kilometers, and 6 kilometers. The computer power goes up as the square of the distance. The number of moving models that can be displayed on a screen is limited by the processing power of the computer. Display resolution of the computer screen influences the fidelity to the desired image, In these examples, high, medium, or low. A number of things can affect pixel color, including the color of the object itself, light, texture, atmospheric effects, and other factors as well. Texture is an image mapped onto a polygon. And finally, level of detail refers to the amount of detail in an object or scene. This can be based on the distance from the viewer. The less detail, the less power the computer uses. Some of these factors affect polygons, others affect pixels, and some influence both. But all require trade-offs in the design of a computer-generated visual world. Let's see how some trade-offs among these various factors affect the final image and use polygon processing power. For our purposes, let's assume a fixed polygon capacity at a fixed frame rate. This virtual battlefield could be constructed in different ways. Let's increase the viewing range. Because more CIG computer power is required on the background, less is available for the foreground. With database density, if we use our power to add detail on the terrain, like trees, shrubs, roads, fences, and so on, we'll have that much less available for movable and static models like houses and vehicles, and vice versa. If it's important to increase the level of detail on the houses, one option is to shift some polygon processing power from the vehicles. All of the preceding examples were based on the same fixed polygon capacity. We can also make trade-offs based on pixel processing power. In the next examples, we're assuming a fixed pixel capacity at a fixed frame rate. Display resolution affects the fidelity of the image, which in turn plays a large role in recognizing and identifying targets. If you don't need high resolution, there may be more power to use on other things. If texture isn't used, less processing power is required, but the image can change radically. You may want to add a feature like drifting flares, which will consume additional pixel capacity. The same pixel capacity can be used in different ways on the same scene. Just because we use pixel capacity to its best advantage doesn't automatically mean we're doing the same with our polygon capacity, and vice versa. Trade-offs in both areas have to be addressed at the same time. But even with the best trade-offs, a scene can destruct from overload when more things are happening than we can process in real time. A real problem in networking, because we can't know when, where, or how many other players may appear. Even though we can't always avoid overload, there are two major things we can do about it. First, we can minimize it by designing the visual database to the system capacity. And second, we can manage overload so it's not so noticeable when it occurs. There are several overload management tools that can be used. Level of detail is sometimes one of them. By simplifying forms and textures, the overall scene is simplified, and computing power is released for other things, more models, for example. We can also reduce the viewing range, meaning fewer polygons and pixels need to be calculated. This may be an answer if all the action is relatively close in, and it gets rid of blinking hills. Or we can decrease the frame rate, so there are fewer frames to calculate. The difference between the normal 30 Hz and this version at 15 Hz is not too noticeable and could be less distracting than flashing models and disappearing terrain. Depending on the application, any one or combination of these techniques could work well. All the trade-offs we've mentioned and more have to be taken into account at every step of the design process. But if you've exercised all your options and still aren't getting the results you need, some important decision-making is in order.
If we have an image generation requirement that exceeds a particular piece of hardware that we're working with, we're simply either going to have to accept less resolution of one form or another, or purchase a higher power image generator. Those are your two choices.
Networked simulation systems can be excellent tools, but if we hope to achieve the optimum results at the best cost, trade-offs are a necessary part of life.